We're talking this evening about the laws of science. And I think there's some clear implications relating to the creation-evolution controversy just from the fact that there are laws that govern the universe. There are laws that we experiment, we see, we experience here in Texas, and they operate the same way in China, and as far as we can tell throughout the universe. And in what I would consider the golden age of science, when Sir Isaac Newton and Kepler and men like this studied and taught science, made incredible discoveries and progress from their day, they considered the laws of science emanating from God, that they were thinking God's thoughts after Him. That bothers a lot of people today. Of course, there's still a lot of scientists who think exactly that way. But men like James Shea have difficulty with that concept. He's editor of the Journal of Geological Education, and he says the concept is anachronistic. This concept of laws of science, this is old-fashioned, it's belonging to a past era, in that it originated at a time when the Almighty was thought to have established the laws of nature and to have decreed that nature must obey them. And then this fellow who's a scientist says it is a great pity for the philosophy of science that the word law was ever introduced. And that just absolutely amazes me, that someone considers himself a scientist, thinks that way. The truth of the matter is, science was born from the concept of believing that there were laws that we could discover. There were laws that had been laid down by a creator that we could repeat and experiment with and come to know from repeated use. Prior to that time, it was all magic and demons and mystery, and you couldn't repeat things, you couldn't explain things. But once they understood that there were laws that governed the universe that we could study and discover and repeat, then we can have science. That's where science came from. But now then he's recoiling from that because of the implications. If there is that kind of law of science, maybe there's a lawgiver, and that doesn't fit his philosophy. Albert Einstein would certainly be considered one of the great men of science, and he certainly believed that there were laws, that it wasn't a pity that we thought about it in terms of laws. And he's speaking here about thermodynamics, and we'll talk some about that this evening. Don't let the word scare you. This is a concept that I assure you understand, though you may not use that terminology. And he says, this is the only physical theory of universal content concerning which I am convinced that within the framework of the applicability of its concepts, it will never be overthrown. Here are laws that we can depend on. Now, we talked about what it took last night to become a law and to be proved scientifically. This fits all of those criteria perfectly. There are a number of laws of thermodynamics. The first one we'll look at basically says you can't create something from nothing. You didn't know that, did you? Just out of nothing, you don't get anything, do you? It's sometimes called the law of conservation. Matter, energy can be interchanged, but neither can be created or ultimately destroyed. You burn something up, but it just changes its form to vapor and smoke and so forth. Isaac Asimov is an atheist, recently deceased. Someone said he's probably written more books than he's read. I think that's an overstatement. Over 600 books, science fiction as well as mainline science. But one of the leaders in the field, and he's speaking about this concept and says the law is considered the most powerful, most fundamental generalization about the universe that scientists have ever been able to make. This is the one that we have more confidence in. He says this law is one that no one knows why, and it is a mystery, and it's interesting to talk to scientists when they begin to speculate about why energy is conserved, and they can't break this law. But he says no one knows why it's conserved. All that anyone can say is that in over a century and a quarter of careful measurement, scientists have never been able to point to a definite violation of energy conservation. Now that's, again, what it takes to become a law. This is true either in the familiar everyday surroundings about us, or in the heavens above, or in the atoms within. Now that's a very broad scope, and sometimes people will say, well, yes, but it doesn't apply to atoms, or it doesn't apply to the heavens, and even the atheist acknowledges that it certainly does. You can't get something out of nothing. Well, how did we get something? The present concepts of naturalism say that all things came into existence out of present laws, but this most powerful generalization about the universe says you can't get anything out of nothing, and we know from the second law that it's not eternal, it all degenerates. This is the principle of uniformity. We explain everything in terms of what we see now, and yet how can you do that? That, of course, is a theory. We don't know that from a fact. And Asimov is wrestling with this conflict. How do you explain what we have, which we know can't be eternal, when you can't get something from nothing if you don't have the supernatural? Natural law says that won't work. Well, he's wrestling with that when he says, perhaps in an infinite sea of nothingness, if you can imagine that. It sounds like there's something, doesn't it? Globs of positive and negative energy in equal-sized pairs are constantly forming. I think he's already gotten off track from his nothingness there. After passing through evolutionary changes, combining once more and vanishing. And we are in one of these blobs in the period of time between nothing and wondering about it. And this is supposed to be science, when the most fundamental generalization about the universe is that you cannot do that. And so here we have this principle of uniformity, which he's trying to sustain, that says everything came into existence as a result of present laws, and then that fundamental generalization that says you can't do it, the principle of conservation. The second law is just as much, actually more, confrontational to the concepts of natural origins. And the second law basically says things go downhill. You didn't know that either, did you? We all understand that very well. It's called the principle of entropy increase, and scientists like to say things just to make you work at it a little bit. Entropy is the measure of disorder, and so it says basically the system runs down or wears out and tends toward disorganization, which we all understand. Entropy is the measure of that disorder, and so the disorder increases. That's it's a backwards way to look at it, but that's the concept. Asimov, again, is describing this when he says another way of stating the second law, then, is the universe is constantly getting more disorderly. Viewed that way, we can see the second law all about us. We have to work hard to straighten a room. Left to itself, it becomes a mess, again, very quickly, very easily. Even if we never enter it, it becomes dusty and musty, and how difficult to maintain our houses and machinery and our own bodies in working order, and how easy to let them deteriorate. Is this news to anybody? No. We don't call it the second law, usually, of thermodynamics, but what we do when we think of it in that context and we measure it precisely is prove that there are no exceptions to this, that this is always the way it works. He continues describing it, saying, in fact, all we have to do is nothing, and everything deteriorates, collapses, breaks down, wears out all by itself, and this is what the second law is all about. We buy a new house, and over the years it gets brighter and shinier and adds new rooms and gets more ordered. No, it goes the other way, doesn't it? And sometimes winds up looking like this. This is what we observe if we watch long enough, isn't it? But the concept of natural origin says it's going the other way. It's defined, evolution, by Dobzhansky as a directional process that gives rise to increase. Precisely the opposite. In the book Cosmic Evolution, notice the subtitle, The Rise of Complexity in Nature. This is the naturalist description of what's going on. Eric Chison of Harvard is quoted here on the book cover. Along an era of time starting at the Big Bang, Chison depicts cosmic evolution in a wide range of systems: particulate, galactic, stellar, planetary, chemical, biological, cultural. Over time, all these systems, be they manifest in worms, human brains, or microchips, become both more complex and more ordered. Everything in the universe is going uphill. But the second law that we observe and have tested and have proven says it goes the other way. And so we have the theory which says it goes uphill, and we have the law that says it goes downhill, and they're very much in conflict with each other, and which one ought to prevail? I think that's a fairly easy question unless you have philosophy dominating your science. Well, when we present this, there's an obvious problem that people see, but there's an answer that we inevitably get on the college campuses that is supposed to answer this dilemma. And that is that the earth is open to the energy of the sun. And we have all of this energy bathing the earth, and with that extra energy, you can overpower this tendency to degeneration. And of course, you can make things go uphill. You can make water run uphill with a pump, engineer energy. You can have the acorn that grows up to the oak tree. Of course, it eventually dies and deteriorates, but it is bathed in the energy of the sun, and you can see that overpowering the tendency to degeneration. And so the idea is that as long as you have energy, then you just forget the law. Actually, there's some that think that and have taught that. It's nonsense. John Ross of Harvard, in Chemical Engineering News, addressed that point directly when he says, ordinarily, the second law is stated for isolated systems. That's the way it's defined. That's the way you have to make the equations balance. You have to deal with it in terms of the closed system. Something else is going to mess up the equation. But the second law applies equally well to open systems. I mean, the fact you've got the sun shining on you doesn't mean you're not going to get old and deteriorate, does it? Or is that we know that's not the case with buildings. Arnold Sommerfeld, who wrote the book Thermodynamics and Statistical Mechanics, says the quantity of entropy generated locally cannot be negative, irrespective of whether the system is isolated or not. Entropy, the measure of disorder, has to be positive. Disorder increases. Again, that backwards approach. George Gaylord Simpson of Harvard makes, I think, a very common sense statement in his introduction to biology when he says, the simple expenditure of energy is not sufficient to develop and maintain order. Now, if you're going to develop and maintain order, make something go uphill, yes, you have to have energy. But that's a necessary requirement, not a sufficient requirement, though. You have to have more than that. He says a bull in a china shop performs work, but he neither creates nor maintains organization. Does that make sense? The work needed is particular work. It must follow specifications. It requires information on how to proceed. And so not only do you need energy in order to overpower this deterioration, you need information. You need particular energy specifying how things proceed. And that's very obvious when you look at the simple cell. That's what we're talking about in terms of origins here. Carl Sagan, certainly not a friend of the creationist, acknowledges that the information content of the simple cell has been estimated at around 10 to the 12th bits. How much is that? Comparable to about 100 million pages of the Encyclopedia Britannica. Now that's a lot of information. Where did it come from? It didn't come from the energy of the sun shining down on the earth. That doesn't produce 100 million pages of information. Information itself, like physical systems, deteriorate and go downhill. And every exchange that we know anything about is going downhill with extra information that you add to the system. Together with energy, you can make it go up, but you can't make it go up if you don't have both energy and information. We can illustrate that, for example, with mutations, which ironically is supposed to be the raw material for the upward process of evolution. But actually it's a degeneration of the information. As the cell replicates, something gets messed up, and all of this 100 million pages worth of information in the simple cell, something in there is not replicated perfectly and something goes wrong. One illustration of that is the Texas blind salamander. Now, it doesn't hurt it that bad, since it can't see anyway down in the cave, to have lost its eyes. But this mutation is not really an upward process. It's downhill. It's losing information. I was testifying before the textbook committee in Austin a couple of years ago, along with Dr. Bishop, who was head of the biology department at the University of Texas. And the two of us were speaking to the school board, and one of the school board members asked Dr. Bishop, is there an example of evolution that we can see in the world today? You say this is proved, it's a fact, we ought to be able to see it. And he said, well, yes, the blind salamander in Texas is a great example. It has adapted to its environment. It's evolved to fit that situation. And so they said, Dr. Patton, what do you have to say about that? I said, well, yes, it's changed, but it's lost its eyes. There's tremendous amount of genetic information in an eye, and he lost it. This is downhill, not uphill. Now, if he comes up with headlights down there, then he's evolving. And so one of the school board members said, well, Dr. Bishop, can you think of a better example than that salamander that went blind? And he got mad and got up and left. But all of the changes that they point to are like this. Degenerative, and they say, well, look, he adapted. Well, yeah, but it's a downhill process. Mutations decrease information. Richard Dawkins was presented with this dilemma recently, and he was asked, can you think of any kind of a change that is not a decrease in information? Illustration of this second law. And it was focused on information. Would you like to know what he said? Give me an example of an increase, any kind of a mutation or evolutionary change that increases information. Well, I'd like for you, instead of me just telling you what he said, let me let you listen, and we'll listen to the interviewer asking him the question.
Professor Dawkins, can you give an example of a genetic mutation or an evolutionary process which can be seen to increase the information in the genome?
There's a popular misunderstanding of evolution which says that fish turned into reptiles and reptiles turned into mammals, and so somehow we ought to be able to look around the world today and look at our ancestors. We ought to be able to see the intermediates between fish and reptiles, or between reptiles and mammals. We ought to be able to see fish kind of on the way to becoming reptiles. But of course that's not the way it is at all. Fish are modern animals. They're just as modern as we are. They're descended from ancestors which we're descended from. Way back 300 million years ago, there would have been an ancestor, which was the ancestor of modern fish and the ancestor of modern humans. And that ancestor, if you could have been there then, you could have seen the first steps towards a fish, say, coming out onto the land and becoming something like an amphibian. But that was a long time ago. You wouldn't expect to see that today.
Isn't that brilliant? I mean, you really got a good example of something that increases information. I'll guarantee you he wishes he had a better answer, but that's the best he can do. He's, of course, had a lot to do with, along with Carl Sagan, the SETI program here in the United States, which I think very well illustrates the problem. Billions of dollars being spent looking up into the sky for what? Some kind of information. Some kind of a dot, dot, dash, dash that would indicate there's intelligence out there. And if we saw this information, that would indicate intelligence in outer space. We haven't found it. Still trying. But why don't instead we just look down the microscope, as many have, and recognize what's there? As he tells us, Sagan tells us, there's 100 million pages of the Encyclopedia Britannica. That's a whole lot more than just a few dots and dashes. If you walk along the beach, as we pointed out, and you see John loves Mary, that's enough information to say this is from intelligence, but they see 100 million pages of information, and no, that just happened. That's not intelligence. But if we saw a few dots and dashes, that'd prove intelligent life in outer space. Does that make sense to you? It just shows the power of the prejudice against something besides natural origins. So, when we talk about this degenerative law, the second law of thermodynamics that pervades the universe, the simple explanation, well, it's open to energy of the sun, provides a necessary requirement to overcome the degenerative process, but it's not sufficient. You also need information. And in that simplest cell, you need an explanation for 100 million pages worth of information in the simplest cell we know anything about. Okay, you got part of the answer, the energy. Where's the other part of the answer? Where did the information come from? And I've asked that question on college campuses all over the country over and over again. And you know what they say? You just heard the answer. They don't have one. Oh, we got energy from the sun, yes, but that's not really the answer, is it? That won't do the trick. Not only do we see this in the world around us, I think we see evidence of this degenerative process everywhere we look. One place the evolutionists wouldn't expect to see it is in the life of the past, and we'll talk more about that when we speak of the fossil record Friday evening. But it is a degenerative process, and while we have all of these little books that show upward increase of the animals and the little horse charts and the graduated man charts, that's not what you see in the fossil record. Even Stephen Gould acknowledges this when he says the sweep of anatomical diversity, all the different forms of anatomy, how many, well, you've got a maximum right after the initial diversification of multicellular animals. In other words, when it starts, that's the way it is. It's more diverse than it is now. The later history of life preceded by elimination, not expansion. It's going downhill. And it was larger in the past, and we have degenerated. Now, you've read that in your textbook, right? Don't think so. But this textbook acknowledges in this geology text that mammalian life was richer in kinds of larger sizes and had a more abundant expression in the Pliocene than in later times, and you can find expressions like that in all of the periods. Let's just look at a few examples that would help demonstrate this point, beginning with Louis Leakey, who's supposed to be one of the icons of evolution. If you saw Gorillas in the Mist, he's the hero of evolution, who really wasn't, and we'll talk more about that later. But Time magazine, a number of years ago, says he was scouring the gorge since 1931. Over the years, he's unearthed the bones of an ancient pig as big as a rhino. Y'all have all seen pigs like that? A 6-foot-tall sheep, flat-top skull of a wrecked nutcracker man. I think that was a big ape. Pig as big as a rhino. Or you could make a killing in the bacon business, couldn't you? This is a picture of one of those pigs from the Dakota School of Mines. The one on the right is the fossil pig. And if pigs were this big, how big were the rhinos? Here's one from India, 20 feet tall. Back to Louis Leakey's finds, illustrated here in Time magazine, we see the fossil ram that was found there in Africa compared with a modern ram in the background. You can see what's happening here. It's going downhill, isn't it? But of course, man has gotten larger over the years, and we know in the last 50 years that there has been a pretty dramatic increase. Most biologists would say this is because of our knowledge of nutrition and vitamins. We have more to eat and better food to eat. It's not the kind of change that they're looking for to explain evolution. There's been about a 6-inch increase on the average in the past, less than 100 years, actually. But if you increase 6 inches in 100 years, in 200 years, a foot, and in 400 years, 2 feet, and a couple of thousand years ago, we were below zero. This is much too fast and not the kind of thing they're looking for. Plus, when we look at the fossil record, we see evidence of large people, which they don't always tell you about. This is Turkana Boy, found by Lewis's son, Richard. He was 5'6", but the interesting thing is he was 9 years old. They can tell from the teeth. We probably have some 9-year-olds here, but I strongly suspect they're not 5'6". We have, Cro-Magnon man averaged 6'6" in height. Two fossils in Italy found a couple of years ago over 8 feet. They were big in the past. Not all, but many of them were. We excavated this donkey from near Lubbock, Texas, several years ago, 9 feet tall at the shoulder. That kind of messes up the little horse charts, doesn't it? That's not going to work too well, but so they leave him out. In the same area, we excavated a bison with a 12-foot horn span that stood about 11 feet tall at the hump. Y'all have all seen bisons that tall? No. But that's the way it was in the fossil record. And we see the little armadillos running around. You can see the normal-sized one in the foreground here in this page from a geology textbook. But notice the writing at the bottom. This was 9 times larger than present-day armadillos. Now, when you see these little graduated horse charts and you see the graduated man chart, that is supposed to give the illusion everything's getting bigger. Let me tell you something. You're being lied to. Because every paleontologist knows the very opposite is true. Just a few years ago at the Society of Vertebrate Paleontology, which I'll be at next week down in Houston, by the way, their annual meeting, they were talking about an armadillo that they found. It was the size of an elephant. That's the way it was described. In fact, in 2004, this news release came from the BBC. Here's a Stone Age elephant twice. Now, elephants are big today. But here were elephants twice as big as the largest modern African elephant. Bones of other large animals, rhinoceros, all of them were bigger. And here we see at the inset the huge tusk for these elephants that were twice as large as modern-day elephants. We're looking here at a fossil turtle that looks for all the world like modern turtles, except this one was 14 feet from one side to the other. You see many 14-foot turtles running around. Here, compared with a 7-foot basketball player, he is dwarfed. From down Big Bend, and it's not because it's from Texas, but there is a big crocodile compared with a modern crocodile here, 50 to 20 feet. National Geographic had a special that dealt with the large crocodiles that were seen in the fossil record just a couple of years ago. And this is typical when you look at the fossil record. We're looking here in the center at a 14-foot shark jaw. That's a good-sized shark, but wow, look at that thing from the fossil record. Jaws is dwarfed by such. We see the great white illustrated. That's a pretty good-sized shark, but nothing like the fossil sharks. We have one of the teeth from the large fossil shark back in our artifact room. Most of us are familiar with our little beavers. They can be pretty aggravating as they go around chewing on branches. But think how aggravating it would be if they were 10 feet long, as is the case in the fossil record. Again, a page from a geology textbook. Here we see a picture from the Field Museum of Natural History in Chicago of the 10-foot beaver. Science reported just a few years ago a real mighty mouse, 8 million years ago. The buffalo-sized rodents roamed in Venezuela. In fact, Science News reported him as Ratzilla. Glad they're not around. This from 2005 in Syria, a camel foot that indicated a camel, according to the BBC, double the size. Do you get the point? I mean, this just goes on and on and on. This is the way it was. One of my favorites, here described in Wikipedia, is the demon duck of doom. 8 feet tall, 500 pounds, carnivorous. Don't want one of those things after you. Kind of reminiscent of a movie scene.
Fairly alarmed here.
That would alarm us, I think. From Australia, killer kangaroos once roamed Australia. Science News says they had teeth that crunched through bones, sliced off flesh. They were enormous. Why haven't you been told this in your textbooks? Because it doesn't look like evolution, does it? It looks like devolution, devolving. And so they don't tell you about it. The ground sloths we have today, 5 or 6 feet long, but 20 feet long, and this is what the textbook says. I've seen them twice that size. This one is from the Price Museum of Natural History in Utah. I measured the hand portion. It was 18 inches. They just found one down in Argentina. The hand was twice that size, which would indicate someone twice as big as this one. One of the more common fossils, especially with dinosaurs, are the cattails. We see those in Texas quite often. How tall are cattails? You might see them in Texas, pretty good size, 8, maybe 10 feet. 120 feet tall is not unusual in the fossil record. You can see the little man for scale here. You don't see that today, but it's typical in the fossil record. We're looking here at a modern cycad, a type of fern here in the Dakota School of Mines. I put the quarter up here for scale. This is their sign. But we look in the fossil record, and here from the book Fossil Cycads, true cycads were apparently quite large. One fossil from Japan is a stem over 4 feet in diameter. Today it's like a little, maximum 18-inch fern. Bugs were big. All the bugs were big. Most of them are found in the Pennsylvanian. I think that's because it's not a time era. It is a swamp area where you find a lot of bugs. But notice, not a few of them, not some of them, all of them. This is a beautiful fossil of a dragonfly, 27 inches in wingspan. Do you get the point? Just on and on and on. I excavated a cockroach from near Oblong, Illinois, several years ago, 1.5 feet long. The wife wouldn't let me bring it in the house. It's a rock. No, it's a cockroach. When we look back in the fossil record, obviously we see big things when we look at dinosaurs, and these were enormous. Here's Seismosaurus, maybe 150 feet long. There is one representative of the beakneck family that's still around that remains from this group of animals. Maybe killed off by people that understood what we see when we look at Jurassic Park. We'd rather not have those things around. The only representative today is the tuatara from New Zealand. Same family. He's about 8 inches long. Hadn't evolved a whole lot. What we see in this whole world around us is not an upward process, but a downhill process everywhere, even in the fossil record. Now, animals going downhill, is that because of the second law of thermodynamics? I'm not sure I can prove that, but it sure smells like it. I mean, everything else is going downhill, and we certainly see that indicated in the fossil record. At least it gives me a chance to combat the picture, the lie that's presented with these little graduated horse charts, leaving out my 9-foot donkey, and the graduated man chart, leaving out the Turkana boy, and all of the fossils that are inevitably bigger in the past. It's all going downhill. I think it fits a consistent picture. As we're thinking about laws, we want to concentrate and have on the ones that are unquestionably laws. Unlike those things that can't be observed or repeated, that are claimed to be laws and aren't. And the point we've tried to make is you see it everywhere. Certainly in the world around us, we have this from our own experience, and we see it even in the fossil record, or certainly we see a downhill process. I think we see it very obviously in the earth itself. As we look around us rather dramatically, we see erosion taking place. Is this going uphill or downhill? It's much more downhill than we realize. In fact, we spend a good bit of time measuring how much sediment is being transported by the rivers to the oceans. And you can put the little measuring devices in the mouths of the rivers and multiply times the flow, and you get an idea of how much sediment is being delivered. 27.5 billion tons is being delivered to the ocean by the rivers every year. Now that number doesn't mean a whole lot, but let's put it this way. That's enough to fill a freight train that would reach all the way to the moon and halfway back. Every year, dumped in the ocean. Now that's not an uphill process, is it? It's dumping the continents in the ocean. Now, there's a lot of mass in the continents, and you can do some pretty quick, simple calculations to see how long this could go on, and we wouldn't have continents, and it's not very long. The Earth's been here supposedly 4.5 billion years, and you couldn't do it at this rate more than about 14 million. But, of course, we've still got big continents. But it couldn't have been going on anything like the age of the Earth. Well, of course, if you move it over here, we're told about the principle of isosity, and you push down here and it pumps up over here. But you can do those calculations and check those simple explanations, and they don't work. Sometimes they try to explain it in terms of seafloor spreading, and it accounts for about 1/8 of the total problem. It's going downhill, just like everything else. When we look in the heavens, I think we see one of the most dramatic examples of this process. While the evolutionist says everything in the world is going uphill, everything in the world and the universe around us is doing just the opposite. You see astronomers that talk about stellar evolution and galactic evolution, and everything they talk about is going uphill, when the fact is it's opposite. You go out on an average night, a good observer can observe about 100 of these little shooting stars, we call them. Little bits of matter that are burning themselves up as they crash into the atmosphere. Here is probably something that's come apart in the universe and now is coming into the atmosphere and burning itself up. This is dramatically downhill. Some of them are very dramatic, as we see the meteor showers. This is a linoid meteor shower. This is one that approached the sun several years ago and came back around this way, coming apart and then crashing often into a heavenly body. Here, like the moon, on our side, on the backside, unprotected from the earth, its atmosphere, it's just been beat to a pulp. Again, this is not an uphill process. Something's come apart, something's crashed in, it no longer is in existence, and we see this on Mercury, and we see it on Mars. We see huge craters, and this is evidence of downhill everywhere we look. We look up into the sky and we see the beautiful comets, and here's one, the Hale-Bopp comet, that is coming apart, which is what we see comets do. This is the Ikeya-Sika comet from a number of years ago, similar to the Saho 6, one of the sun grazers. Notice NASA's description: a family of comets created by successive breakups from a single large parent comet which passed very near the sun in the 12th century. This comet, known as Saho 6, did not survive. Doesn't sound uphill to me. Fred Whipple of the Smithsonian Astrophysical Observatory, one of the leading experts on comets in the world, in his book Mystery of Comets, says comets tend to split in pieces, particularly when they're near the sun or Jupiter, but also when they're quite undisturbed in space. Some comets seem to tire out and die. Isn't that a surprise? Here's a picture of one that tired out, died, split into many pieces. This is the Shoemaker-Levy comet of '94. NASA provided us a dramatization of what happened. It crashed into Jupiter, each piece with the force of many megatons of an atomic bomb, just boom, with huge force, crashing in. Again, the thing that came apart went downhill and then crashed into the surface. Here on Jupiter's moon Ganymede, we can see this string of craters which indicate something came apart and then boom, 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 the parts crashed one after the other, 13 fragments. We see this on the moon. Here is the streak here that indicates this string. Why are the craters lined up? Because something has come apart and then the parts crashed. And it fits the picture that we see everywhere we look in the heavens. The thing that we see most obviously when we look at the sky is the sun. We're told that it's dissipating 4.5 million tons per minute in thermonuclear reactions. We do know it's, quote, figuratively, burning up, dissipating energy out through space, not only through the normal stellar processes, but through the prominences and flares that you see blasting out on the side. Here's a huge one, blasted out, compared in mass to the Earth. Huge. 4.5 million tons per minute, and then boom, other things like this. In addition to that, the solar wind dissipates another 1 million tons per minute. And so we've got at least 5.5 million tons per minute. That's not helping it a whole lot. Now, there's a lot of mass there, and it's not going to go out tomorrow. But it's a downhill process, and pretty dramatically downhill. Now then, multiply that times what you see when you look out in the sky. Most of what you're seeing out there is stars, billions and billions of stars that are dissipating millions of tons per minute. What's going on in the universe? It's dramatically going downhill. And that's with just the normal stellar processes. When we look at things like the planetary nebula, beautiful fireworks in the sky. Here's a star that just blew up, 10 to 30% of its mass, blasted into an outer shell from a dying sun-like star, producing the planetary nebula known as the helix. Here's another beautiful planetary nebula, boom, like God's fireworks. But it's not an uphill process when something blows up and leaves this spray of sparks. Is that uphill or downhill? Some of them are just spectacular and even symmetrical as they blast themselves out of existence. This dying star throws off shells of glowing gas. Here the radiation floods out in the surrounding gas, causing it to fluoresce. And when we see these glowing gases, sometimes we're told, well, look, it's heating up and condensing. Now, what's happening? It's blasted out, and the shock of the blast excites the particles like we see in the fluorescent lights here and causes them to fluoresce. It's an indication of an explosion. And here NASA says this radiation floods out into the surrounding gas, causing it to fluoresce. Over the next several thousand years, the nebula will gradually disperse into space and the star will cool and fade away. That's what we see. But the planetary nebula are just kind of pitiful compared to the novas and the supernovas, which not just blasting 30% of the mass, but completely blast themselves out of existence. This is one of the last ones that we saw, 1987. And we see in the inset the way the star looked one night, and then beside it the way it looked the next night. Tens of thousands of times brighter overnight. Now the normal star is like the sun, 5 million tons per minute. And then 10,000 times more than that as it blasts itself out of existence. We see the remnants of some of those explosions. Here are one of them in the Crab Nebula. As NASA said, this is the mess that's left when a star explodes. It's beautiful. This one happened to be observed. A number of cultures observed and recorded this explosion that took place in 1054. And we know of the Chinese and the Arabs, the Native Americans, possibly two others, but these recorded it and saw it. So we know what's going on here. Now we got glowing gases. Maybe it's coming together? No. It's blowing up. Number of these supernova remnants are seen. This is a spectacular one, blinding flash, which the concentrated power equals that of 10 quadrillion suns. I mean, the sun is degenerative. 10 quadrillion suns. How do you get an uphill process when everything you see is just not only degenerative, but dramatically degenerative? Here's the description of NASA. This is N49's cosmic blast. Scattered debris from a cosmic supernova, an explosion, lights up the sky just like fireworks. We can get some predictions and maybe some ideas about how long this has been going on from the fact that these supernova remnants appear about once every 25 years in our galaxy. And we're not sure why, but it's pretty regular. And over the past 100 years, we've seen this happen. Actually, further back than that, of course, 1054 gives us a pretty good range of observation. This is the conclusion, and I don't know of anyone that argues with it. That's what is indicated. Well, if it's one per 25 years, we can see immediately how many we ought to be able to observe if it's this old or if it's that old. We can make some predictions, which is the way science tests models. If we're looking at 1,000,000 years, then we ought to be able to see 40,000 of these things at one every 25 years. Pretty simple. Well, no, because some of them are behind gas clouds, and some of them are near novas that get dissipated when it blows up. So we grant every possible exception and even exaggerated a little bit. And they'll say, well, you still, maybe not 40,000. You ought to be able to see over 7,000. Okay. But what if we're looking at only 7,000 years? Well, that's a very different picture. We would predict one every 25 years, 280, maybe some of them we couldn't find behind gas clouds, something like 270. Very different predictions. 7,000, less than 300. Which one fits the facts best? What do we actually observe, which is what science is about? So far, we've been able to find 260. Isn't that interesting? But we see when we look at the news and we look at the propaganda that we're inundated with, articles like this. This is from USA Today. Hubble telescope captures the birth of a star. Boom, here came a star. Well, you read the article and say, well, it actually takes well over 100,000 years for this to happen. And, okay, well, nobody saw it last night, which is the impression you get when you look at the headline. And we're not seeing it happen. We're seeing things that they say infer that it's happening, or at least that's the impression they like to leave you. The experts will tell a different story. Here from Science Magazine, 1990, we have yet to directly observe the process of stellar formation. Nobody has seen that, in spite of these misleading headlines. But we're pointed here in Discover Magazine to the stellar nurseries. Like every night we can see new stars popping out, and of course we should. You calculate how many are out there, you ought to be able to see them forming, because they're just a mind-boggling amount. We're pointed to the Orion Nebula. Spectacular. Glowing gases. Shocked from an explosion. But here's a nursery. Here's where they're just popping into existence, or should be. We hadn't observed it, but this is where it's happening. Just trust us. Here's what NASA calls a star factory. Why? Well, we've got glowing gases. Oh, well, here we've got glowing gases. Yeah, but now we saw this explode in 1054. We know what this is. And so when we see this, that can't be... We got to explain it somehow. And all we can see is glowing gases, and when we know how the glowing gases got there, we know it's not star formation, it's blowing up of a star. J.C. Brandett addresses the problem in his book, Sun and Stars. He says, contemporary opinion on star formation holds that objects called protostars are formed as condensations from interstellar gases. Okay, you turn loose gas from an aerosol can in this room, and the gas just comes together in a little ball up here, doesn't it? Or does it? What happens? It doesn't condense, it spreads out. I mean, we know that. You see the smoke from the campfire come up, and it doesn't gather together in a little ball. It spreads out and dissipates. But here they're imagining that it condenses. Well, the second law says things are going to get more disordered. It's not going to get more ordered. He goes on to say this condensation process is very difficult theoretically. In other words, we can't make it work on paper. No essential theoretical understanding can be claimed. In fact, some theoretical evidence argues strongly against the possibility of star formation, and of course it's not theoretical, it's the second law of thermodynamics that says it ain't going to happen. Oh, but you've got gravity that attracts, yes, and that you start compressing gases, and what happens? It heats up and it pushes back, doesn't it? You've got expansive forces as well as the attractive forces, and you can measure both of them. The expansive forces are 60 times greater, and so it's going to come together. Not when the expansive forces are 60 times greater. Yeah, well, I know gravity works and there's an attraction, but measure the two and see which one's going to win. Very powerful evidence argues against this. And while it'll tell you in your earth science textbooks, we know exactly how this happens, the authorities know better. Here, Abraham Loeb for the Harvard Center of Astrophysics. The truth is, we don't understand star formation at a fundamental level. Now, if you're an earth science teacher in high school, you can tell folks, we know. But if you're head of the Harvard Center for Astrophysics, you have to admit, no, we don't have a clue. And I think we know which one is more dependable. Here's another reference from Science 2002. Stars are among the most fundamental building blocks in the universe, and yet the processes by which they're formed are not understood. So don't let the teachers fool you. They don't have... How do you get gas which spreads out to come together? And they don't know. Godfrey Bernbridge, a more frank, very leading authority in our nation on astronomy, says, he's director of the Kitt Peak National Observatory, if stars did not exist, it'd be very easy to prove this is what we expect. They're burning up. They're burning up in quotes. They're dissipating energy. It's all going downhill. And it's been going on billions of years. There ought not to be any. How do you get them together? Well, you can't in terms of what we know today. All of the authorities that I'm quoting are atheists. They're naturalists. I want to make an exception and refer you to the statement by Dr. George Mulfinger, who has his PhD, recently deceased, but had a PhD in astronomy from Syracuse, but was a creationist. Now, I want to make that distinction. And of course, he referred to the fact that one of the problems is that it's unscriptural. Genesis 2:1 says, all the hosts were finished. All the stars and the host of them were finished when God created. So he says, really, there are only three problems, he says, regarding star formation. The first is it's unscriptural. And the second is it's never been observed. And the third is it's theoretically impossible. But aside from those three problems, he says it's a real winner. Which I think is a pretty good analysis. But even those who are atheists say very similar things. We've been talking about stars. Let's multiply the problems in forming stars by hundreds of billions of times, and we see the problem we have explaining galaxies, which not only have the problem of forming the stars in them, but forming the organization, the collectivity of stars. How did they get together when the second law says everything goes the other way? Martin Rees, astrophysicist, writing in the Dallas Morning News a few years ago, says the most basic questions about galaxies are still not understood. If galaxies didn't exist, we'd have no problem explaining that fact. That sound familiar? And like a refrain. It's not supposed to be coming together, not naturally. And we see beautiful formations up here, these pinwheel spirals like M51. This forms when the center part turns faster than the outer part, like the ice skater pulls in their arms and spins faster and slows down when the arms of these galaxies act like that. The spiral-shaped wave patterns from the galaxy's center whirl around the core 3 times as often as those 6,000 light years out, says the team. All but guarantees the galaxy's bright inner pinwheel is destined to wind itself up. Now, it doesn't take many turns to just completely wind itself up into this amorphous disk, not like the spiral arm disk. Well, how fast is it winding itself up? Well, it's pretty fast, just a few 100,000 years, not the 20 billion or 15 or 13 billion that they proposed for the age of the universe. It looks like it hadn't turned more than once or twice. Just a few 100,000 years is the most you can get for this. And what really gets difficult is when you look at what's called the barred spiral. And here's this straight bar right across the middle, and it hasn't twisted at all. Just half a turn, and that'd be messed up. And that would take just thousands of years, and there it is. And why in the world do we have bars in the middle of these spirals like this? I think it may be that the Lord's just looking down and saying, nah, 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 nah. You can't explain this. Because just in a short period of time, it would be destroyed. It wouldn't be like that. When we have seen more through the Hubble telescope, it's been anticipated. Now we're going to explain natural origins, but the further we look, the more difficult it's gotten. Here reported in the Dallas Morning News, astronomers, the Space Telescope Science Institute released the deepest ever view of the universe Tuesday. Long duration exposure, reached out to a point just a few million years from the Big Bang. Look way out to just right. We can almost see the beginning out there. And what do we see? A wide range of galaxies. We don't see baby galaxies. We don't see forming galaxies. We see completely mature sizes, shapes, and colors, everything that you see everywhere else. Looking back to the beginning, you should see it gradually forming. Not at all what we see. This was reported by Gemini Observatory, showing how this should have developed theoretically from the little baby galaxies, the little seeds, finally to the more mature galaxies that we see with the spiral arms, and pointed out that, well, here's the headlines. The faintest spectra ever raised glaring questions. Why do galaxies in the universe appear so mature? It's massive and mature right back to what they call the beginning. Richard Cowan, University of California at Davis, comments on this. He says, galaxy formation theory is in peril. Over the past 18 months, several teams have found so many massive galaxies from this early epoch that the theory is being stretched to the breaking point, several astronomers say. In other words, we can't explain this. It just flies in the face of what we predict. Notice the comments of James Trefil, who's professor of physics at George Mason University, one of the more famous astronomers in the country. He says, it seems the more we learn about the basic laws of nature, and he's not talking here about Sunday school literature. It's the basic laws of nature, what we're talking about tonight. The more those laws seem to tell us the visible matter, the stuff we see, shouldn't be arranged the way it is. That is, if it's old. That is, if you're trying to do it naturally. You can't do it that way. It doesn't work. The stuff we can see shouldn't be arranged the way it is. There shouldn't be galaxies out there at all, and shouldn't be stars out there in the galaxy. On top of that, if there are galaxies, they shouldn't be grouped. Stars are a problem. Groups of stars and galaxies are a problem. Now we got groups of galaxies. Just multiply the multiplication. Galaxy clusters, the Hercules cluster of galaxies, organized. It just multiplies beyond our imagination. The problem of trying to explain it naturally. We hear a lot about this solar system, and especially in the earth science textbooks, they say this all condensed from the nebular cloud. This here's the dust, and it spun around, and it is condensed into these planets with the sun in the middle. Not a very good fairy tale, which is about the best you can say about it. All kinds of problems. First, the sun has 99% of the mass, where the planets have 99% of the angular momentum. Now, if you're a physicist, you understand, this is all condensing out of the same cloud, and here's the mass, and it's not moving very fast, but these things out here that have virtually none of the mass are just going up a storm relative to the sun. How did they get going so fast when the great mass is just plodding along? You know, that's not going to work. This has a slow spin. The planets have rapid orbital motion, which is not going to condense naturally out of a cloud. Sir Jeffreys of Cambridge says, I think all the suggested accounts of the origin of the solar system are subject to serious objections. The conclusion in the present state of the subject would be the system cannot exist. That is, naturally, if it's been there for a long time. And again, there's another refrain. More recently, 2007, just a couple of months ago, this fairly up to date, and they're talking about planet formation theories. And what they find when they put this on the computers is, okay, you get some boulders and some rocks here that are supposed to come together to form a planet, and what happens? The boulder goes right to the sun. This planet formation theory has been a stumbling block for 30 years, which, of course, you've read about in your earth science textbook. No. The reason is that boulders tend to fall into the star in a celestial blink of an eye. There are enough uncertainties that planet formation is not going to be an open and shut case anytime soon. He said, we don't know how that collapse into a planet actually occurs. In spite of the fact your earth science textbook tells you just that happened, it just condensed out of the cloud. No, we don't know, and when we try to explain it, we fall flat on our face. Same thing is true with the moon, and we could spend a whole evening talking about the problems there, but here, from nature, many models have been proposed for the formation of the moon. No one has succeeded in showing how the formation had formed successfully. Jack Lissiter, with the NASA space program, says, all in all, developing a theory of lunar origins that makes sense of the data proved very difficult. The best explanation was observational error. The moon did not exist. One of the ways to test a model is to see how the predictions take place. If stars didn't exist, that's what we'd expect. There shouldn't be galaxies. They shouldn't be grouped together. The solar system shouldn't exist. The best explanation is the moon didn't exist. But you read the textbook and it's like, we can explain it all. What can they explain? It all flies in the face of their naturalistic explanation. The basic laws of nature say it will not work. And so when we back off and look at the two models, and we see the obvious prediction of degeneration and decay by the creationist as defined by what we read in Genesis, degeneration, decay, imposed as a consequence of sin. All right, let's test that against what we see and see what fits. That's what we see. The evolution model says things are going to go uphill, and they have great faith, and everything from microchips to brains, it's all going uphill. But what do we see in the world we live in? Your own experience with your houses and your cars and the bodies. And is it going uphill or downhill? Well, we know that. When we look at the life of the past, we see dramatically things were bigger and now then they have gone downhill, which they don't like to admit, but it's just as obvious as it can be. When we look at the universe around us, when we look at the sky, we see everything from stars to the face of the planets to the comets to the planetary nebula, the just stars blowing themselves out of existence, galaxies, everything is going downhill. That's not what they predict. Now, just be honest. Which model explains what we see best? Now, I don't think it's a hard question if a person's honest. Let's think before we conclude about some implications of this and allow Isaac Asimov to acknowledge what he sees as a real problem. He says, as far as we know, all changes are in the direction of increasing entropy, increasing disorder, or increasing running down, randomness. Yet the universe was once in a position from which it could run down. Now the natural processes, everything we see, say it goes downhill. How did it get up? It had to be up from which it could run down, but natural processes say you don't go that way, it goes this way. How did it get into that position? You see, the second law of thermodynamics says there had to have been something besides the natural processes we see to explain what we're looking at. And there's no way around that. H.J. Lipscomb is an atheist, writing in Physics Bulletin, but faces the issue squarely. He says, I think, however, we should go further than this and admit the only accepted explanation is creation. I know this is anathema to physicists, as it is to me, but we must not reject a theory we do not like if the experimental evidence supports it. And it's not, again, the Sunday school lesson that's telling, this is the law, the laws of science that govern this universe, and it says you can't do it naturally. It doesn't work. You can't explain anything that you see in the universe around us, and it certainly doesn't fit the picture that we see on this earth. The experimental evidence says, obviously, the creation model works better. I want to conclude with a statement by two very brave men. They are creationists, but they're the authors of the textbook that's used in virtually every undergraduate program in thermodynamics in the country. Every university in the state of Texas that I know, I've been able to check, and that's most of them, use their textbook. Now, people will say, maybe, all right, you're a hard-rotten geologist, archaeologist, what do you know about thermodynamics? Well, I may not know a whole lot, but these fellows do. They wrote the book. We see the second law of thermodynamics as a description of the prior and continuing work of a creator. naturally you cannot get it here where it can then be seen to be going down as we do now. You can't. And so that second law that says everything goes down says natural law is not going to account for this. You've got to have something beyond the natural in order to see what we're seeing and see things go downhill. It also holds the answer to our future destiny and that of the universe. It's going down to destruction. And that's clearly implied from the laws of nature, from these fellows who really know what they're talking about. I think that is a powerful bit of evidence and should be obvious to people who are willing to look.